Assalamualaikum warahmatullahi wabarakatuh and good day. Okay, last week we have learned about atom and atomic bonding. So this week we will learn about structure of crystalline solid. We learn about how the atom is arranged in a solid. Atom is arranged in a repeating or periodic array over a large atom distance. Okay, almost all metals, many ceramic and certain polymer have crystalline structure under normal solidification condition. Okay, this is different between crystalline and non-crystalline. Crystalline is material that the atom is repetitive in a periodic array. Okay, for non-crystalline is material that the atom is not arranged in a repeating or periodic array. Okay, term that you need to learn on this topic is lattice and unit cell. Okay, lattice is lattice is how you see that how the atom is arranged, and unit cell is the block of atom which repeat itself to form the small lattice. Okay, there is for metallic crystalline structure. Okay, almost all metal tend to be densely packed. Okay, why? Why it is it's densely packed? It's because first sometimes there is one element is present, so all atomic radius is the same. So it will automatically arrange by itself in a most dense way. Okay, second is for metallic bonding. Okay, metallic bonding, although it is contain two elements, okay, it's still non-directional. So for non-directional, the atom still can arrange in a periodic way. Okay, 60% of metal have either one of these structure. Okay, BCC, body center cubic, face center cubic, and also hexagonal close pack. Okay, as 90% of metal is arranged on this way. So for this topic, we will focus on this type of crystal. Okay, body center cubic, face center cubic, and also hexagonal close pack. Okay, this is the difference between BCC, FCC, and HCP. Okay, we will learn more later. Okay, the other term you need to know on this topic is APF, atomic packing factor. Okay, APF, atomic packing factor, is volume of atom in a unit cell. Okay, you know that for what is for unit cell. Okay, volume of atom in a unit cell over volume of a unit cell. Okay, for example, for BCC, if it is BCC, the atomic packing factor is 0.68. For FCC and HCP, the atomic packing factor is same, which is 0.74. So you know that FCC and HCP have the same number of atomic packing factor. And okay, later we will learn on how to calculate this APF. Okay, the other term you need to learn is about the coordination number. Okay, coordination number is the number of the nearest neighbor for atom, or the atom that is touching with one atom. Okay, how many atom is touched with a single atom? This is the coordination number. Okay, we start with simple cubic cell. Okay, simple cubic cell is can be imagined as a cube with an atom on each corner. Okay. Actually, there is no common material with a simple cubic structure, but as this is the simplest structure, so we will always learn with SC. Okay, the only element that display SC, okay, simple cubic in a regular temperature and pressure are polonium, okay, radiative. Okay, for simple cubic cell, okay, we look at the coordination number. Okay, coordination number is the number of atom touched with a single atom. So for SCC, okay, if this is one atom, okay, the atom that touch the atom is 1, 2, 3, 4, 5, 6. So the coordination number is 6. Okay, next we go to BCC, body center crystal structure. Okay, for a unit cell, okay, there is one atom at the center and 1/8 atom at each corner. Okay, example of atom with BCC, body center cubic, is chromium, iron, and also sodium. Okay, we look at the coordination number for BCC. Okay, for one atom, it touching with 1, 2, 3, 4, 5, 6, 7, 8. Okay, so for the coordination number for BCC is 8. Okay, next, we're going to calculate how many atoms in a unit cell. Okay, so as I said before, there is one atom at the center and 1/8 atom at each corner. So the number of atom for BCC structure is 1 atom plus 8 times 1/8 atom. So 2 atom in a unit cell. Okay, let's go to the first example. Okay, molybdenum at 20 degrees C is BCC and has an atomic radius of 0.14 nanometer. Calculate the lattice constant A in nanometer for the cube edge of the molybdenum unit cell. Okay, this is one unit cell. Okay, and it is BCC. Okay, so for unit cell, okay, one side of unit cell, okay, the length is A. And then for this example, you know the radius for an atom, so you need to find the relationship between A and R first, and then you can determine the length of A. Okay, so for BCC, okay, as you can see in here, for this side to this side, okay, it is equal to 4 radius. Okay, 1 radius. Okay, for this 1/8 atom here, and 1 radius for this 1/8 atom here, and for this atom it is 2 radius. Okay, so for this side to this side is equal to 4r. Okay, next we need to find the relationship between A and R. Okay, you know that one side is A, so for this point to this point is equal to A square plus A square and then square root. So we get here, it is equal to square root of 2A. Okay, next, okay, for this side to this side, okay, is equal to, okay, again using the theorem Pythagoras, okay, this side is square root of 2A and this side is A. So for this side it is square root of 2A square plus A square. So it's equal to square root of 3A. So using this relationship, you know that 4R equal to square root of 3A. And then A equal to 4R over square root of 3. So for this example, okay, A equal to 4 times 0.14 nanometer over square root of 3. So it's equal to 0.323 nanometer. Okay, second example, calculate the atomic packing factor for the BCC unit cell, assuming the atom to be hard sphere. The atomic packing factor, APF, is volume of atom in a unit cell over volume of a unit cell. So okay, for BCC, okay, the atom is, okay, the number of atom is 2. Okay, how to get 2? Okay, I think I've showed before. Okay, this for the center one is 1 atom, and we also have 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 times 1/8. Okay, so 1 plus 8 times 1/8 is equal to 2. Okay, the volume of atom is 2 times 4/3 pi r cube equal to 8.378 r cube. And for A, okay, for A, you already know that A equal to 4r over square root of 3. So the volume for a unit cell is equal to A cube. Okay, A cube is 4r over square root of 3 power of 3. So we got here that this the number is 12.317 R cube. So you know now the volume for atom, and you know also the volume for a unit cell. Okay, using the formula for APF, okay, V atom is 8.378 R cube, and volume for unit cell is 12.317 R cube, so equal to 0.68. Okay, this is how to calculate the APF for BCC. Okay, next we go to FCC, phase center cubic. Okay, FCC. Okay, an example of material with FCC is aluminium and also gold. Okay, FCC. The arrangement is there is the atom at each surface and another atom at the corner. Okay, this is the arrangement for FCC. So we calculate. We need to calculate how many atom in for each unit cell. Okay, so for the corner, okay, corner is 8 times 1/8 atom, and for the surface it is okay, C surface times 1/2 atom. So it's equal to 4 atom for one unit cell. Okay, next the relationship between A and R. Okay, for FCC, okay, you can see that for this surface, okay, it's equal to okay 1 R at each corner and 2 R for the atom at the face surface. So this is equal to 4 R, and the relationship for A, okay, A. And that side is also A. So from this corner to this corner, the length is square root of 2A. So the relationship is 4R equal to square root of 2A. And then A equal to 4R over square root of 2. And then for the coordination number for FCC, okay, for each atom, okay, imagine for atom at the center, okay, so we can for each atom, okay, the number of atom that is connect with the atom is 12. Okay, for example, for this atom, okay, 1, 2, 3, 4, okay, 5, 6, and then the other side is another 6. So we got 12 atom for the coordination number. Okay, next part for this topic is to label the labeling convention. Okay, we need a labeling convention for pointing a point, for a direction, okay, to show direction, and also to show a plane for a lattice or unit cell. Okay, for point, to locate any point in a lattice, so we use just a Cartesian coordinate system. Okay, as example, starting with x, y, and z. So for this point, it is 1, 0, 0. For x is 1, 0 in the y direction, z in y direction. And then for this point is x equal to 1, y equal to 1, z is equal to 0. So it is 1, 1, 0. So it's very simple. And then the convention is x. Y is direction to the right, x is the direction coming out of the paper, and z is the direction toward the top. Okay. Okay, let's go for the third example. Specify point coordinate for all atom position for a BCC unit cell. Okay, BCC is a unit cell with one atom at the center and the other atom at the corner. So okay, draw a Cartesian coordinate system, and then we can write the coordinate for each point. So, okay, 1, 0, 0, 1, 1, 0, 0, 1, 0, and for the center one it is half for each direction. So it is half 1/2, 1/2, 1/2. Okay, I think this is this to point to pointing any point in a coordinate in a unit cell is very simple. Just use the simple coordinate Cartesian as you already use in other subject. Okay, for the next part is the direction index. Okay, the direction index. Okay, so this is to get the line between 2 points. Okay, so example for this point, okay, is from 0, 0, 0 to the location of 1, 1, 1. Okay, how is the convention for the direction is first is you need to state the vector. Okay, so the vector read all projection in term of z dimension in the x direction, y direction, and z direction. And then okay, for example, for this line, okay, for this line, the direction is okay is go to x equal to 1, y equal to 1, and z equal to 1. So the direction for this line is 1, 1, 1. Okay, and then we go to the direction for the blue line. Okay, for the blue line here. Okay, the direction for the x direction is equal to 1. Okay, y direction equal to 0, and the z direction equal to half. Okay, 1, 0, half. Okay, this is the vector for this line. But when you got the value below 1, okay, you need to adjust to the smallest integer value. So for this one, okay, you need to time 2, okay, to make sure that all is here in an integer. Okay, so after we time 2 is equal to 2, 0, 1. So the direction for this line is 2, 0, 1. Okay, in case you got direction that is negative 1, 1, and 1. So for negative 1, we use a overbar. Okay, so for overbar is represent a negative index. Okay, more example. Okay, one example. Okay, we go to the direction for this line, R line. Okay, the direction is going toward the x direction directly, and no vector for this y and z. So the direction for this line is 1, 0, 0. Okay, for s, okay, the vector is 1 for x and 1 for y, okay, and 0 for z, 1, 1, 0. Then the direction is 1, 1, 0. Okay, for this line, okay, 1 vector for x, 1 for y, and 1 for z. So the direction is 1, 1, 1. Okay, for this line for m, okay, 1 for x and for y direction, the vector is half. For z direction, the vector is 0. So 1, half, and 0. And then again, as I stated before, if it is smaller than 1, you need to adjust to the smaller integer value. So we need to time to 2. So you get as we can name it into 2, 1, 0. Okay, for this direction, okay, for n, okay, the direction in the x vector is negative 1. The direction in the y vector is negative 1. And the direction for z vector is 0. Okay, negative 1, negative 1, 0. So for the direction, it is 1 cap, 1 cap, and 0. Okay, and more example. Okay, 1, negative 1, negative 1. Okay, this is a five example. Okay, I think try to do it yourself first, and then we will discuss in the next lecture. But for this part, I think I will use it as an assignment. Okay, you need to submit this part, and This is all for the attendance for this week. Okay, next, to name a plane in a unit cell. Okay, using the lattice unit cell. So what we use to name a plane is using the Miller index. Okay, Miller index by the William Hollows Miller. What we use to name is using the intercept point for each vector x, y, and z, and then we will name it after the reciprocal or fractional intercept of the intercept point. Okay, we go to the first example. Okay, if you get the Miller index of 110, okay, how is the plane? So we calculate the reciprocal for this plane. Okay, 1 over 1, 1 over 1, 1 over 0. So it is for x direction 1, for y direction is the interception is 1, and for z vector the interception is infinity. This means that there is no interception in the z direction. So you know that this is how the plane look like. Okay, it intercept x at point 1 and intercept y at the point 1 and no intercept at all at the z direction. Okay, so this is the plane for the Miller index 110. Okay, next, okay, if you get the plane but you need to name it. Okay, so first you need to know where it is intercept. So intercept at point at x at the point 1, intercept at the y at the point 1, and didn't intercept at point z. So it intercept at the infinity. So again, determine the reciprocal for this plane. So 1 over 1, 1 over 1, 1 over infinity, it is 110. So you didn't need to reduce anything because it is all integer. So Miller index for this plane is 110. Okay, if the Miller index is 200, okay, how is the plane? Okay, again, state the Miller index 200, and then find the reciprocal for this plane. So for the x is it at 1 over 2, for y is 1 over 0, and for z is 1 over 0. So it intercept at x direction at point 1 over 2, but it didn't intercept at the y and z. So how the plane look like is like this. Okay, it's only intercept at x direction at point 1 over 2. Okay, so it didn't intercept at the y direction and also z direction. Okay, let's go for the next example. Okay, draw the following crystallographic plane in cubic unit cell. Okay, 101, 221, 111, negative 10, 3, negative 2, 1, 0, 3, 0. Okay, we go to the first first example. Okay, 101. Okay, the step is easy. First, find the reciprocal. Okay, 1 over 1. Okay, for y direction 1 over 0. For z direction is 1 over 1. So we know that it intercept at x direction at point 1. It didn't intercept at all at point y, and or it will intercept at the infinity. So it's the same. And then for the z direction, it intercept at point c is equal to 1. Okay, just draw the plane. Okay, intercept at point at x direction at point 1, intercept at z direction at point 1. Okay, next example, 2 to 1. Okay, find the reciprocal 1 over 2, 1 over 2, 1 over 1. So we know now that it is intercept at x direction at point 1 over 2, intercept at y direction at point 1 over 2, and intercept at the z direction at point 1. So just draw the plane 1 over 2, 1 over 2, and 1. Okay, this is the plane for the Miller index of 2 to 1. Okay, next example. Okay, for Miller index 1, -1, 0. So a circle is 1 over 1, 1 over -1, and 1 over 0. So the intercept point is at point x equal to 1, y equal to -1, and z equal to infinity, or it didn't intercept at direction z. So this is the plane, intercept at point 1 and also -1 for the y direction. Okay, next example, 3, -2, and 1. Again, find the circle, 1 over 3, 1 over -2, and 1 over 1. So this is the intercept point, x equal to 1 over 3, y equal to -1 over 2, and z equal to 1. Okay, this is how the plane look like. Okay, next example, x value index for x for 0, 3, 0. Okay, again find the reciprocal, 1 over 0, 1 over 3, 1 over 0. So it didn't intercept at x and y direction, so it's only intercept at y equal to 1 over 3. So this is how the plane look like. Okay, last plot for this week is the volume density. Okay, volume density is mass of atom in a unit cell over volume of a unit cell. So for example, okay, the density of copper, okay, calculate, we can, after this we can see how to calculate it. So example, if you use this formula to calculate, you can get the density of a copper is equal to 8.9. But if we measure it, it's equal to 8.94. Although there is some error, it is still in a good agreement. Okay, so last example for today. Okay, copper has an atomic radius of 0.128 nanometer and an FCC crystal structure. Compute its theoretical density in gram per centimeter cube and compare the answer with the measured density, 8.94 gram per centimeter cube. Okay, to solve this question, first find copper. Okay, for copper, the atomic number is 29 and the atomic weight is 63.55. So you know that, do you know the atomic weight? Okay, 1 mole of copper equal to 63.55 gram. And you know that for 1 mole, the number of Avogadro, or the number of atom, is 6.02 times 10 power of 23. So you know that for 1 atom, okay, is equal to 63.55 over 6.02 times 10 power of 23. So for 1 atom, the mass is 1.056 times 10 power of -22 gram. Then you already learned how to determine the volume for unit cell. Okay, for unit cell, equal to a cube. Okay, and A is equal to 4R over square root of 2. So for volume of for unit cell is equal to 4R over square root of 2 power of 3. So it's equal to 22.627 R cube. Okay, you know the radius for copper is 1.28 times 10 power of -8 centimeter. So you get now the volume for unit cell is equal to 4.74 times 10 power of -23 centimeter cube. So you can now calculate the density. Okay, mass of atom is 4 times 1 over, for a unit cell in, because it is FCC, okay, For a unit cell, it's a content of 4 atoms. Okay, so you need to time the weight to 4. Okay, 4 times 1 over 1.056 times 10 power of negative 22 gram. Okay, this is the mass of cuprum atom in a unit cell. And then you already calculate the volume for a unit cell is equal to 4.74 times 10 power of negative 23. So by calculating it, you get the density is equal to 8.90 gram per centimeter cube. So it's very close agreement with the measured density 8.64 gram per centimeter cube. Okay, next, polymorphism. Okay, polymorphism is the ability to exist in 2 or more crystal structure. Okay, example is for titanium, carbon. Okay, it is depend on the temperature and pressure. Okay, so temperature and pressure can change the crystalline form. As example for iron, okay, in low temperature, it exists in a PCC. But when you heat it up, so it will change into FCC. But if you heat it further, it's come to BCC condition again. Okay, how to determine this BCC or anything? So you just use the XRD machine, X-ray diffraction technique. Okay, by using the X-ray, okay, they will get this figure, and we can determine the material using the peak for the line. So if it is 211 or anything, so they can determine the type of crystalline. Okay, lastly, amorphous material. Amorphous material is non-crystalline material. Okay, non-crystalline material is the material that lacking in long-range atomic order. Okay, example for silicon oxide, okay, SiO, you can see here the arrangement is totally systematic. Okay, but for non-crystalline, okay, the arrangement is not systematic. So sometimes it is 6 atoms, sometimes we will get another type of atom. So for this type of material, it is non-crystalline. Okay, some material can behave in a crystalline and non-crystalline. Okay, this is the example for silicon oxide. Okay, that's all. The learning outcome is first, draw unit cell for FCC and BCC. And second, calculate atomic packing factor and density for BCC and FCC unit cell. And lastly, use labeling convention for crystallographic point, direction, and plane of a cubic cell. Okay, that's all for today. Thank you.